So the big question we are still sort of following the history of, right? The small bit, the small stuff of what we're doing is learning about interesting constructions and some very interesting theorems. But if you step back a little bit, and with this simplicity and hypersimplicity, what we did was follow in Post's footsteps. Right? We have zero jump. Those 2 degrees we have examples of, and I guess we accidentally have an intermediate degree, but that's not quite purposeful yet, right? The Post's question was, do there exist intermediate degrees? And his strategy was to define these different sets, which try and come up with a characterization to show that, well, if I have a characterization, if a set A has property P, then first of all I can show that there exists a set A with property P, and second of all, property P implies it's intermediate. That's what he wanted. So that's sort of the program we're on that didn't work with simplicity or hypersimplicity, but we're getting lots of nice constructions out of it. And the same is with the next theorem. Every non-zero CE degree contains a hypersimple set. So that at least shows that hypersimplicity is not the right notion for being an intermediate degree, because in particular there exist complete hypersimple sets. So what do we do? Well, we take a non-computable CE set, right? Any CE degree contains a CE set. If the CE degree is not a computable CE degree, then it contains non-computable CE sets. And we want to show that there exists a set that is hypersimple, that is Turing equivalent to this A. Now you could imagine all sorts of complicated constructions required for this, but it turns out that a very natural set to look at that in general gives you interesting information about this set A does the trick, and this is the so-called deficiency set. Let me first non-computable CE set. So in particular, I'm introducing some notation before giving the definition of the deficiency set. Non-computable CE, so in particular, is infinite. Infinite CE set can be written like this, with no repetitions. Right? An infinite CE set is the range of a total computable function, and that's exactly what this is. So from this we can now also define approximations. Right? Our sigma 1 approximations, more and more things are in there, and we let it agree with the enumeration that's given by this computable injective function. Okay, so now back to the comment I made before I started introducing this notation. There exists this set which gives us some really nice information about A, which does the trick for the theorem, the deficiency set. So, what is the deficiency set? Well, if you're going along in this enumeration, right, as S goes to S plus 1, you add one more element to your set. Now, what happens sometimes, you add this one more element to the set, and now, up to and including this new element, the set in the initial segment is complete. So this is sort of a good stage. You just added the last thing to the initial segment determined by this. At other stages, you now add something very large, and in a little while you add something very small. And so then the large thing you added, the initial segment determined by it wasn't yet finished. So those are the so-called division stages. The stage is S, such that there exists a stage later on, such that a number gets enumerated that is less than AS. Right? The stages S are exactly those stages that you enumerate something in, where the initial segment determined by this last thing hasn't finished yet, hasn't stabilized yet. There's a question?
No, it's good.
So the non-deficiency stages are exactly the good stages where you enumerate something in and the whole initial segment is done. So this is, I think under that picture, an interesting set related to A. Two things to observe, of course. We want to see, first of all, that D is hypersimple, and second of all, that B is Turing equivalent to A. Hypersimplicity, we know, is equivalent to not computably dominated. So, in order to show one, we say, suppose G dominates the increasing enumeration function of D complement. Remember, P subsum set was the increasing enumeration of this set, which made good sense as soon as the set is infinite. Now, this set definitely is infinite, because if the deficiency set of some set A is finite, then almost every state is a non-deficiency state, so you go past all the deficiency stages, and now every new element that enumerates, everything that came before is already in its final stage, and that clearly gives you a computation method for that set. So D bar is infinite, D is infinite. Suppose we have a G that dominates it, then the claim is that X is in A if and only if X is amongst the first GX things enumerated into A. Right? First we observe, right, we want to see that no such G exists. So suppose such a G exists, this set here on the right is computable. So then A became computable, but we picked A to be non-computable. Therefore, this equivalence would show that such a G does not exist. Then we need to see that this is true, right? That if we had a G that dominates this function, then this is true. But what would G of X be? Right? We know then that P of D bar of X is less than or equal to G of X. So G of X is an upper bound for the X element of D complement. Right? So G of X is greater or equal than the first X element of D bar. What are the elements in D bar? Those are the non-deficiency stages. Right? Elements in D bar are non-deficiency stages. So if you have had X non-deficiency stages, then X times it was the case that you added an element to the set A, and everything up to and including that element has stabilized in A. Well, the first time this happens, you have a number which is greater or equal to 0. The second time it happens, you have a number that is greater or equal to 1. The X time it happens, you have a number that is greater or equal to X. So after X non-deficiency stages, an initial segment of A has stabilized that is greater or equal to X. which is to say that if you look at x, certainly the initial segment of A up to and including x has stabilized at that point. So if you have this domination, then by just counting the number of non-deficiency stages you have passed, you know that a sufficiently large initial segment of A has stabilized, and therefore its equivalence is true. But this is exactly what a number. The first number here are the natural numbers. The first non-deficiency state says, okay, here we have an AS that gets enumerated, and this initial segment has stabilized. The next non-deficiency stage clearly cannot be caused by enumerating something less than or equal to AS. So you need to have something bigger. So now a strictly bigger initial segment of A has stabilized. And the third time you find that you are at a non-deficiency state, again a strictly larger initial segment of A has stabilized. If x times a strictly larger initial segment of A has stabilized, then the now stabilized part is of size at least x plus 1. That's all that's going on. So that leaves 2 to show that D is Turing equivalent to A. Turing equivalent means D is Turing computable from A, and A is Turing computable from D, and we're essentially done already. On the one hand, D is clearly Turing computable to A, because if you enumerate the next element, then you can just check, did we already enumerate all the elements that came before it? And if the answer is yes, we did already enumerate all of those, you are at a non-deficiency stage. If the answer is no, you did not enumerate all of those yet, then you are at a deficiency stage. So that's how you decide D from A. The other way around, by the arguments just given, if you want to decide if x is in A, you just have to go sufficiently far out that you are past x non-deficiency stages. And if you have the set of deficiency stages, you can easily just start checking how far you have to go before you have passed x non-deficiency stages. And if you have passed x non-deficiency stages, then, then computing the initial segment determined by that s is long enough that it has stabilized at x. So I guess what I'm saying is, if you have D, then you can compute a big enough G that does it. Or equivalently, okay, in one we showed G is not computable, but such a G is clearly decomputable, because this function is. Okay. Wonderful, so our hopes quashed yet again. Hypersimple sets are not a characterization of intermediate degrees. Can we do better? Well, not really. So again, still working on post-program. Okay, hypersimple doesn't do the job. Simple doesn't do the job. Maybe what we need is effectively simple. Unfortunately, if A is effectively simple, then K Turing reduces to A. So all effectively simple sets are complete, i.e. not intermediate for sure. Right? Hypersimple sets, if there are intermediate degrees, then there are intermediate hypersimple sets, effectively simple, that won't happen at all. It's a pretty nice construction to do this. Okay. Proof. Okay, we have Ks, a sigma 1 approximation of K. We have As, sigma 1 approximation of A. A, effectively simple by F. Right? Effectively simple meant that if the eth CE set is greater than f of E, it has non-empty intersection with A. So this f function gives an upper bound on the CE sets in the complement. Then from this we can define this function theta x, and this function theta x shows up more often. It just says, okay, look for the least s such that x is in Ks. Right? We have this sigma 1 approximation. Of course, this function theta depends crucially on which approximation you took. But it says just look for the least stage where x has appeared in K. Right? If x is not in K, then this diverges because you will never find such an s. If x is in K, then you get exactly the size of a computation. So this is the input, and now I want to show that using this, right? How is this theta useful for trying to show that K could be computable from A? Well, one of the ways of deciding K once you have theta is to find a function bounding to theta. If you have an upper bound for theta, then if you have a total computable function that wherever theta is defined is greater or equal to theta, then to check whether something is in K, all you have to do is check whether it is in K sub the index indicated by that function. Right? This theta satisfies x is in K if and only if x is in K theta s. Theta is of course not computable, not total. But if we have a total function that's always greater or equal to this, then you can use the same equivalence to decide K from A. So that's what we want. We want a function that we can compute using A that dominates theta. And the way we do this is to define W h of x. Right? I'm defining a CE set. What does it look like? Well, if x is in K, I do one thing. Otherwise, well, what should it be otherwise? Undefined. Undefined. So undefined and sort of CE set is empty. Right? We're defining a Turing machine that holds on all the things in WH of x. If it's checking this, then indeed, if this is not true, you diverge. You're undefined, which makes the corresponding CE set empty. If x is in K, right? As soon as you know that x is in K, you can compute theta x, and you know you will find the value. And we say this is A naught of theta x up to A f of h x of theta x. So these A super S are the elements of the set A enumerated by stage S. And so what are we doing here? We're looking at which elements have been enumerated by stage theta x, and then the first fhx plus 1 elements in there. Right, if you, this is the first element, so this is the fhx plus first element. And you notice here I use h of x in defining h of x, which of course I can do because of the recursion theorem. So this function h is a computable function. Good. Now I can define the function rs, which is the least stage such that as f of h, this is an x, r of x, h of x is equal to af of hx. Right? What is this saying? Okay, look for the least stage s, such that if you look at the first fhx plus 1 elements enumerated into A at that stage, they correspond to the first fhx plus 1 elements enumerated into A at all. Right? If the fhx, let k be f of hx plus 1, if the kth element of the increasing enumeration of A has stabilized, then the whole initial segment has stabilized, because you can't stick anything in without the kth element changing. So this is really saying, okay, the initial segment there has stabilized. Which of course, right? F is computable, H is computable, but deciding when this is stabilized is not necessarily computable, but it is A computable. If you know what is going to be enumerated into A eventually, then you can check when the corresponding initial segment is stabilized. Okay, so this function r of x is A computable. So now, of course, comes the claim, as explained, what am I looking for? I'm looking for an A computable function which dominates theta, and I just derived an A computable function, so it better dominate theta. And it does, because if r of x is less than or equal to theta x, then what's going on? Then wh of x is contained in A complement. Oh, I've been saying something at least slightly incorrect for a while now about this enumeration being an enumeration of A. It's the enumeration of A complement. Right? These are the movable markers which don't enumerate A, they enumerate A complement. Otherwise, clearly, this doesn't make any sense. Everything I said still makes sense though, because as you're enumerating A long, then you know if you can compute when the complement has stabilized, if you can compute when A has stabilized. So that works out. R is still A computable, and because R is still A computable, if it dominates theta of x, we're still in business. But we clearly need this to be the complement, because here we know something about. If wh of x is contained in A complement, and A is effectively simple because of the function f, then it should be the case that the size of wh of x is bounded by f of h of x. That is exactly the one property the computable function f has, that it bounds the sizes of these functions. But because of this number, which I've got very tired of saying, the number of actual elements it has is f of h of x plus 1, which is one more than it's allowed to have. So this is a contradiction, and that contradiction means that this can't happen, that this set we have here can't be part of A complement. How can it not be part of A complement? Well, it can only not be part of A complement if some of these elements are still going to be enumerated into A later, which means that R of X is greater than theta X. And the proof. Okay, that was a little bit messy by my confusion here. We take these H of X, these WH of X are enumerations, or increasing enumerations of initial segments of our current approximation to A complement, and the whole point is that if they are correct in their approximations, then this is true. And if this is true, then this set is too large. People happy enough with that? So it's kind of a nice construction to see how do you compute K? Well, one of the ways to compute K is to dominate this function theta, and I think in the notes pretty soon there is in fact the next proof I have here uses exactly the same idea again, that we want to have something compute K, and the way to compute K is to dominate this function theta, which says how far you have to go. Okay. So the next theorem is a little bit kind of squeezed in between, but squeezed in between in the sense that it doesn't necessarily fit inside of the whole theme in looking for intermediate sets, but it's just a really nice characterization that I don't want to skip. So we say F is fixed point free if it is the case that for every x, w f of x is not equal to wx. So this terminology is exactly inspired by our thinking about the recursion theorem, right? In the recursion theorem, part of what we were saying in the recursion theorem, or in the motivation up to it, was that finding fixed points of functions is often very interesting, and of course not every computable function has a fixed point, right? Function x plus 1 doesn't have a fixed point, but we did show that every total computable function is not fixed point free in this sense, right? That's exactly what the recursion theorem says. Exactly. If you have a total computable function, you can find an x such that phi f of x is equal to phi x. In particular, the C sets are the same. So now you could wonder, and that would be a good thing to wonder about, okay, how complicated are the functions that are fixed point free? And where does the recursion theorem start failing? For what kind of functions? That is exactly what the Arslanov completeness theorem tells you, which is why it's kind of a nice theorem. If A is a CE set, right, which is a shame, you wouldn't want these sort of requirements in there, they are essential, but it kind of fits in our whole theme that computable sets are very nice, the CE sets are pretty nice, the delta 2 sets are still not too bad, but worse, and right, we have a collection of sets that get better, worse and worse, and the CE sets are decent, so you can prove more about them. In particular, you can show that A is complete. if and only if there exists an f Turing computable from A such that f is fixed point free. Right? It says exactly that in order to find fixed point free functions, you don't just have to go a little up from computable, you have to go all the way up to complete, if you're CE already. Okay, so one direction is really easy. Any guesses for which one?
Start out with A complete.
Pardon?
Start out with A complete.
Start out with A complete. If A is complete, right, it means A computes the holding problem. What use is the holding problem? Well, the holding problem allows you to decide if a C set is empty or not. So, if we have A complete, then we can define this function W f of x to be empty if Wx is not empty, and let's say equal to 0 otherwise, right? The holding problem exactly allows you to decide if the C set is empty. Well, add in a lot more things, but in this case you can. And this function exactly makes it so that one of the two sets is empty, the other one is not empty, therefore they're always unequal. Okay. So now we need to take a function f, computable from A, which is fixed point free, and use it to show A is complete. How do you show A is complete? Well, you need to be able to decide the holding problem, right? Decide Ks. What do we have? We have f, computable from A, such that for every x, W f of x is not equal to Wx. We have Ks, a sigma 1 approximation of K. Given this sigma 1 approximation, we can define this function delta x, which is the least s, such that x is in Ks. Exactly the function you were just looking at. Okay, what else do we have? Well, this is kind of the obvious information the problem statement now gives you. But you have some more, because we remember, or I hope you remember, a function which Turing reduces to a CE set, well, that function has a nice approximation itself. Right? There exists this function f hat that limit-wise computes this function f. Right? What was this function f hat? Well, either you remember that this is called like the limit lemma, that the limit lemma gives you this, which I can hardly remember what the lemma is called. But the intuition for why this is true slowly but surely should become very natural. How do you get this function f hat? Well, you have a sigma 1 approximation for A, and you have this Turing reduction of f to this A. So you can use that Turing reduction with the approximations, with the different approximations of A. And so f of xs is use this Turing reduction with the est approximation of A and compute f. It doesn't quite work because there might be some divergence in there, but that's pretty much the idea. So we have this function f. This function f hat is computable. But also what we have is we have a function f, which is a modulus of f hat, where this function m is computable from A. Right? If you are computing your approximations using approximations of A, you can use A to check whether your approximation is correct in all the places where the oracle actually asks about it, and therefore you can decide. You can use A to decide when this limit has stabilized for a given x. So I think that's all we can squeeze out of our assumptions. And now we're going to use this to do the same trick we just did. Define the right set. Which set is it in this case? W h of x is equal to W f hat h of x delta x. And as soon as I write this, you know what the other case is. Because theta x, right, this gives you a value if x is in k, theta x otherwise diverges, and if you're defining a CE set using a diverging computation, then of course it should be empty. Again, a nicely computable function using the regression theorem. Okay, what is our claim? We now claim, like we did just before, that x is in k if and only if x is in k of m of hx. And on the right hand side here, m is a computable, h is computable. So as soon as we can see that this is true, then we can decide k using a. Right, and this is exactly the same thing as saying that this function m composed with h dominates theta. Because that's defined. Okay, so suppose x is in k and theta x is greater or equal to m of h of x. Well, suppose towards a contradiction that this happens, that theta is bigger. Then f hat h of x theta x is equal to f of h of x. Well, obviously, because m of some input value is exactly how far out you have to go before this limit has settled down, right? The m was the modulus of this limit computation, so m exactly indicates how far you have to go. So if theta is bigger, then you have reached the final value already. This, however, means, what does it mean? It means that WH of x which under our assumption that x is in k is equal to w f hat of h of x of theta x is equal to w f of h of x. That's bad indeed. Right? This here exactly shows that our function h of x is a fixed point of the function f, and we started under the assumption that f has no fixed points. Okay. So these things are a little, there's one big idea in both of these last two proofs, trying to dominate the function theta, and then you just need to come up with the right function that helps you do it, so a little tricky.